I'm Gerardo Adesso from the University of Nottingham, and I want to present you some results which deal with what quantum correlations are useful for. So if you remember, the title of this session is Using Information Physics to Measure and Manipulate, and the question we have to address in the subsequent panel is, what is quantum information really good for? So there is considerable debate, as Max pointed out, about the definition of information, but what I'm concentrating about is on a little bit of debate on the definition of what is quantum. So more or less we all agree that, okay, quantum theory is for the majority of situations, a very good theory to describe the world. So it is the theory that applies at most scales. So in particular, we could say, so everything could be described quantumly. But there are some situations in which a classical description is good enough. Now, in those situations, you could say, okay, then I can explain, for instance, the data of my experiment just by using classical probability distributions. Now, to identify when this happens, contrarily to when instead you really need quantum mechanics, is a considerably hard problem. So in this picture here, Zurek was pointing out at the difficulty of identifying the proper border between what you can describe as the classical world and what is genuinely quantum. So I'm going to study and to describe a little bit research at this border from the point of view of identifying such a border in correlations between two or more systems. Okay? So the question that we have to address is very basic. We have two subsystems and they are correlated. You measure correlations in experimental observations about both subsystems. The question is, you don't know where these correlations come from. Can I explain them classically, or they just arise because there is some genuine interaction between these two systems? So how to distinguish between these two parts? Now, this question has an easy answer in some cases and a non-trivial one in other cases. The easy answer is when overall the state of this global system, A and B, is a pure state. So when it's a pure state, then you really have only two possibilities. Either the two subsystems are completely uncorrelated, or if they have correlations, then those correlations are quantum. So and those correlations are what you typically refer to as entanglement. So the states are non-separable. Every state which is entangled, a pure state, violates some Bell inequality, so you could identify these correlations also from the point of view of non-locality, and that's more or less the end of the story. You have good ways to quantify them, and that's it. If you go to the global state being mixed, so noisy, so in particular you don't have complete information about the preparation of the global state, then this question is not so easy anymore. So in traditional quantum information theory, definition by Werner used as synonyms the term separable, which means not entangled, and the term classically correlated state. So if a state is not entangled, you would say, yeah, it's classical. But the thing is, can we really trust this definition, or maybe we have to revise it? So let's look at separable states, so states which are mixed but they are not entangled, and there are quite a good number of them. And there are some characteristics that you really cannot accommodate for by using classical probability distribution. In particular, one that I will mention is, if I have a state, even if it's separable, most of them, and I make any local measurement on one subsystem, as a result of this, the overall state of the system will change. So in classical probability theory, this doesn't happen. I can make a local probing of a random variable, and this will not induce any kind of modification on the joint probability distribution. But in most separable states, this happens. So in general, states without entanglement, still they have some nature which is non-classical. So how do we account for this? And recent trends in the field are looking at this question and are identifying some types of correlations which are quantum, but they do not necessarily reduce to entanglement. So they can include entanglement, but they are beyond it. And they conventionally go, so they go by the name of quantum discord. So there are several ways to introduce this topic, but in general, this is a signature of quantumness that only is available in correlated systems, and it happens also in almost all separable states. And one way to reveal it is indeed by observing a necessary and avoidable disturbance associated to the effect of any local measurements that I do on my subsystem. So in general, if we draw a picture for a paper on Discord, which ended up on the cover of PRL some months ago, and I can explain it a little bit. So if we have systems which have only classical correlations, then what is possible is that you can find at least one observable that you can measure on one subsystem, such that as a result of this, the state of the system will not change, will remain the same. And so in a certain sense, you can measure this particular observable without inducing any disturbance. And so there's no intrinsic uncertainty associated to that measurement. In particular, that observable commutes with your state. So that's the only case in which you could describe those correlations as classical, because this is what happens in the classical case. Otherwise, if you have any other state, including non-entangled, then whatever local observable you measure, your state will change. So there will be a disturbance induced on your system, and there will be intrinsic uncertainty associated to any local measurement. So in particular, let's see, we could naively, without having to introduce quantifiers, because now there are lots of possible measures to really take this into account quantitatively. So you could say, okay, let me consider a system in a certain state, and let me make a measurement of just one subsystem. And I have to be careful to select a measurement that is minimally disturbing, in a sense that one can rigorously quantify once one chooses a quantifier of information. But if you do that, then those correlations out of the total ones, which are destroyed by a minimally disturbing local measurement, are the quantum ones. And those that remain after this minimally disturbing local measurement in the modified state are just the classical ones. So if there are only classical ones, you find a measurement that doesn't disturb, so all the correlations remain there, they were all classical. Otherwise, all measurements disturb a little bit, find the one which disturbs less, and the amount by which it disturbs a state, you could take it as the amount of quantum correlations between these two systems from the perspective of the object that is being measured. So if you want now, this concept reduces completely to entanglement in the case in which the global state is a pure state. But in the case of mixed states, if you want now, there are not 50, but at least 3 shades of quantumness in the correlations of the two subsystems. So the strongest that you could admit is non-locality. So if I have a state that violates Bell inequality, you could say, okay, definitely I cannot explain this state classically, unless you're Joy Christian. Then if the state doesn't violate Bell inequality, then maybe it is still entangled, like it happens for some Werner states, in the mixed case. And then again, this is not compatible with classical theory. But even if it is not entangled, and you have quantum discord, then again, we have some non-classicality there in the correlations of the system. And out of this, then, there are just very few states remaining, which are then classically correlated, and they actually form a null measure set. So the question is, what is quantumness in these states good for? For sure, we know the states that violate Bell inequality are needed, for instance, for device-independent quantum key distributions, or quantum cryptography, trustful one. States which are entangled are needed, for instance, for teleportation and other quantum communication protocols. What about states with quantum discord? Are they useful for something? Do they offer advantage over states which are basically classical from the point of view of correlation? So this is the question we want to address, and this is the title of the talk, as I said in the beginning. What are these correlations useful for? There's been a lot of work in the recent couple of, 4 years about this, and actually I think it focused more on discord versus entanglement. So people were looking at, can we do things just with discord that we thought we had to do by using entanglement, because discord is a bit cheaper to have. And my interest is not about this, but it's about the border between discord, which is kind of the most general manifestation of quantumness, and just classical states. So wherever I have some quantumness, is it going to give me an advantage over classical systems or not? So we have worked a lot on this topic, and I'm presenting in particular some recent work which is coming from a collaboration with several groups. In particular, there were some experimental groups in Brazil, and there were some theory done, in Nottingham and in Imperial College, but also in Singapore and in Italy with Vittorio Giovannetti and so on. So the experimental groups were in Germany here, Jefferson, and then all these Brazilians between Rio and Sao Paulo. So it's a delocalized collaboration. So we identified a setting where we found a clear usefulness of having quantum correlations in the form of discord already, without necessarily have to have entanglement, in quantum metrology. So this fits in with the title of the session, which is using information to measure. So quantum metrology is something that can be explained quite simply. So the general idea is, what you want is you use some quantum mechanical features you exploit them cleverly to improve the precision available in estimating some physical parameters, in particular parameters which are not associated to any observable, and you have to estimate them somehow indirectly. Okay, and the thing is, what particular quantum mechanical features you need to have? So let's consider one very standard paradigm in quantum metrology, which you could describe as the interferometric one. So phase estimation in an interferometric configuration. This phase could be replaced by frequency, time, or any other physical parameter. So your setting is the following. You have a state in principle correlated. So let's consider at least two parties. You prepare some probe state here, rho AB. Now, one of the systems undergoes some unitary evolution of this form. Now, in this unitary, typically, you know from the beginning what is the generator. So your state is rotated, and you know what is the direction around which it's rotated, typically. And what you want to know is the angle by which it's rotated. So by knowing this generator, you are going to choose some clever probe state. So if I know that rotation is about this direction and I have a pen, I'm not going to orient it like this. I'm orienting like that so I can see the change when the system is rotated. And then at the end, you recompose your states, and then you make the best possible measurement that you can get at the output. And out of this, then it's just a matter of statistical processing. You get a guess, an estimation for the parameter that you don't know. Now, how this works, there's a very nice theory, which has been developed by several people in this room, in particular Bill Wouters, Seth Lloyd, and so on. So if you repeat all this many times, and we are considering independent repetitions of this setup I just described, then the only thing which really matters is you need to prepare some probe states where here the guy which undergoes the transformation has coherence in the eigenstates of the Hamiltonian which is applied at the transformation level. So you don't really need an entangled state between these two. If here is, for instance, sigma z is the Hamiltonian, the best you can do, if these are independent repetitions, is just to prepare, it's equally good if you prepare a maximal entangled state, or if you just prepare here the plus state, 0 plus 1. Then you get the same precision. So you need coherence in the eigenbasis of the generator. And you can quantify your precision mathematically, because basically once you have done your post-processing, then you come out with an estimator, which is a probability distribution. So I think my value is about here, and this is the confidence I have, a variance. So the smaller the variance, the more precise is your estimation. And this variance is seen to have a lower bound, which is 1 over, this is the number of repetition, and this parameter here is a geometrical parameter, which has been mentioned in the list. It's the so-called quantum Fisher information. So this really quantifies how much your probe state is sensitive to the change which is applied at this black box level. I think Bill Wouters gave a very nice geometric interpretation of this. So your Fisher information can be adopted as a measure of precision. You actually can saturate this bound. To saturate this bound, this means that given a probe and given a generator, you just need to find what is the best possible measurement, and this can be determined mathematically. So we will always assume that we do the best possible measurement given the situation. So this is an equality for us. And our figure of merit is, in general, this quantum Fisher information. The higher it is, the better your estimation is working. So what I was saying is that this is maximized by having states with maximal coherence in the eigenbasis of the generator. What if we change the rules a little bit? Okay? Let's drop the assumption that we know from the beginning what is the Hamiltonian. So Alice and Bob in the beginning have to prepare some probe states, but they don't know which direction will their subsystem be rotated about. They don't know the angle, they don't even know the direction in the beginning. So they have to find some resource which could probably work whatever the direction is later revealed to be. How is this possible, and what do they need to do? Okay, so let's study this problem. Let's consider the setting which, at the moment of preparation, they don't know this Hamiltonian. And then later on, once the state has been transformed, the guy here, let's call it Charlie, the evil guy, reveals what is the setting so that they can apply the best possible measurement and then find the estimation. But of course, they cannot go back and change their probe state. So it's similar to situations that we encountered in real life when we have, for instance, an exam. So at the beginning, Alice and Bob have to prepare. Okay, so the probe state is like a preparation. They study a textbook, and they have to be prepared for every possible question. Then they go at the exam, they don't know the question. Then they open up the envelope, and then the test question is revealed. And then based on their preparation, they can formulate the best possible answer. And the question is, we have all been asked in some exam just the particular question we were least prepared for. Okay, so what kind of preparation they need to have so that even the worst possible question for them leaves them able to give an answer and not just completely blank? This is the question, okay? So which probe states guarantee that they're always able to get a precision which is different from 0? So mathematically, what we can do, okay, we say, okay, given a certain choice of the input state, let's quantify the figure of merit in this scenario by considering a worst-case approach. So we define, and that's really a property of the input states only now. So given an input state, we define its interferometric power. So what is its guaranteed precision in a metrology experiment like this as the minimum, apart from this factor, the minimum over all possible choices of the generator of the associated feature information. So the worst case precision that this input probe can allow for. Now, there are some technicalities in this minimum. I have to make it non-trivial, so I'm considering just Hamiltonians which are non-degenerate. Otherwise, you include the identity, and then it's always 0. Okay, so, but let's leave this aside. And let's study this quantity. So this quantity quantifies how this state is able to estimate parameters without knowing in principle what is the direction. Now, this has to reflect some property of the state. States which are better from the point of view of metrology, what kind of resource character do they need to have? And the answer is this. This interferometric power here, we calculated it and we studied it, and it's a measure of quantum discord. So these quantum correlations, even without entanglement, are needed in this case to guarantee a precision in phase estimation, whatever the generator. So if your state is classically correlated, which mathematically means it takes of this form, so then, of course, there's always one possibility that the evil guy chooses the wrong question, and then your state will commute with that Hamiltonian, and your estimation will be completely a failure. 0 precision. Otherwise, if you have quantum discord, then there is always a non-zero precision. And actually, it's not even guaranteed, but the amount of quantum correlations in the form of discord quantify this minimum precision because this quantity here is a measure of discord. Okay? And we have several nice properties, and we can even have a closed formula, which is something nice for people working on discord because several other measures of discord, they are not even computable, not even for 2 qubits. Okay, so that's more or less the conclusion. Then we did an experiment about that. I don't know if I have, how much time I have? 2 minutes. 2 minutes, okay. Very quickly, so we did an experiment with our colleagues in Brazil where we considered 2 classes of states, one classically correlated, one with discord, both at the same purity, so mixed states. Purity depends on this P. And okay, they were very, very high quality preparations of this state. This is done with NMR ensembles. And then what we did, okay, we considered 3 different Hamiltonians, so 3 possible settings for this game, including one which is the worst case for both states. And so rotations about these 3 different axes. And then quickly, okay, these are the schemes to prepare the states. These are more or less the results. So here we are measuring the precision allowed by those states in the different settings. So if the controller Charlie chooses, for instance, sigma z, then it turns out that both the quantum states and the classical states, they offer the same precision. If the Charlie chooses this direction here, then the quantum states offer a better precision. The classical states are always a bit worse. But there is the worst case scenario where, in this particular case, it's a rotation about sigma x, where the classical states commute with this Hamiltonian, so they are not able to give an answer. And the quantum states, it's the worst case for them, but it is guaranteed to be a non-zero precision, which just saturates a lower bound given by their amount of quantum discord, the interferometric power. So here is, we set the unknown phase to pi over 4, and in all these cases, they were able to, I mean, we were able to get the correct guess, apart from this case where the classical states were completely random, giving completely random answer with the variance which, strictly speaking, was infinite, because the states did not get any information about the phase. So every time you have classically correlated states, there is a way to make them fail an estimation. Every time you have states with discord, this will never happen. And how good they are, at least, is quantified by their quantum discord. So in general, if you consider quantum metrology in a worst case scenario, so embrace for the worst, it relies on on this general form of quantum correlations. And I just leave here an advertisement. I don't have time to talk about the actual plan for the FQXi grant, which I got, but I hope we can discuss this in in this week. There's just one postdoc position open about, let's say, quantum cybernetics, and I'm happy to give you more details about it. But if you have a student that is going to finish, let him consider this. Thank you very much.